We already saw that the space of continuous maps between differentiable manifolds is a complete metric space for the weak topology and a Vector space for the strong topology. And we would like to generalize these results for the space of CR maps between differentiable manifolds. In order to do so, we are going to introduce jet spaces, and then we will see that the space of CR maps between two differentiable manifolds is again a complete metric space for the weak topology and again a Vector space for the strong topology. Consider R greater or equal than 1 but less than infinity, so a natural number, and M and N be CR manifolds. An R-jet is an equivalence class of three apples, X, F, and U. X is a point in M, U is an open subset of M containing the point X, and F is just a CR map from U to M. Okay? We are giving the objects, but now we need to give the equivalence relation. Okay, and it's as follows. If we have two objects, x, u, f, and x prime, u prime, f prime, then by definition they are equivalent. If x is equal to x prime, the image of x is equal to the image of x prime, to the image by f prime indeed, okay? And there exists local charts phi of m and psi of m such that x belongs to the domain of the local chart of m, f of x belongs to the domain of the local chart of n, and the expression of f in these two local charts, the expressions of f and f prime, have the same derivatives at the point phi x up to order r. In this case, we say that these three apples belong to the same equivalence class. The definition does not depend on the choice of local charts. Okay, it's intrinsic. It's not difficult to check out. And we say that one of these classes is the R-jet that we are also going to denote with these two notations for the R-jet of f at the point x, either this one or this one. Okay. We are going to denote by J super R of Mn the set of R-jets of maps from M to N. And in this case, we have two natural maps, the source map and the target map. Okay, the source map sends an equivalence class, an R-jet, to the point X. This is perfectly defined because all representatives of the same equivalence class have the same base point. So this is a well-defined map. We can also define the target that sends a representative, that sends a class to fx, where xfu is a representative of the class. Again, our definition of classes implies that fx is always the same for all the representatives in the same class. So in this way, we define a source and a target map. Now, we can define this subset over here as a set of R-jets that have the same base point x. This other subset that could be the set of jets whose value that are in the preimage of y by the target map, and this one, which is essentially the set of jets such that they have x as a base point and x is sent to y, right? Here it should be, yeah, like this. So we can define all these maps and all these subsets of the set of R-jets. Okay, we can identify the set of rjets from Rm to Rm with Rm to Rm, with Rm times Rm times Ra, just by associating to an rjet its Taylor series expansion up to order R, right? If we have a jet, the image by the source map is going to belong to this first component. The image of the target map is going to be here in the second component, and indeed this corresponds to the terms in the Taylor series expansion of order between 1 and R, okay? A is the number of coefficients of a Taylor expansion associated to derivatives of order between 1 and R. Of course, this number is finite and depends on M, N, and R, but it is a finite number. We could even find the function that associates to M, N, and R A, but it's not necessary. What we have is that this jet space is indeed a Euclidean space, right? Okay, we can consider the set of rjets when U is an open subset of Rm and V is an open subset of Rn. We are going to consider the set of rjets whose source is in U and whose target is in V. And that's going to be U times V times Ra. And again, it's going to be an open subset of an Euclidean space because it's a product of open sets. What we can try in order to give a structure of differentiable manifold to the set of rjets is considering local charts and trying by using the local charts to identify some subsets of the space of jets with subsets of the space of jets between open subsets of Euclidean spaces, right? So let's try to follow that strategy. Consider local charts, phi, okay, defined in U, and psi, defined in W of M and N respectively, and we are going to consider this map. The map that sends a jet, an R jet from U to W to an R jet from phi of U to psi of W. Phi of U is P and psi of W is P prime. And what we do is associating to an R jet at the point X the R jet of the local expression of F in the local charts phi and psi at the point phi of X. And since phi and psi are diffeomorphisms, this map is a bijection. Okay, and what we want to use is these maps with different choices of local charts in order to define a structure of differentiable manifold in the set of rjets from M to M. Here we are in a situation that is somehow similar to the one that we saw at the beginning of our course with the tangent manifold. If we have a manifold M that is CR, the tangent manifold is also a differentiable manifold, but it's just CR minus 1. And since we need to consider here we need to consider derivatives up to order R, we need to consider derivatives up to order R, we are going to have an analogous phenomenon for the set of the space of R jets between M and N. We are going to use these maps over here as local charts, and then we have to check out that the coordinate changes are indeed diffeomorphisms. And what's going to happen is that if M and N are CR plus S manifolds, since we are considering here derivatives up to order R, analogously as it happens for the tangent space, the space of R jets between M and N is just a CS manifold. We are losing R degrees of differentiability when we consider R jets. Consider a manifold M a CR manifold. We have that these two manifolds over here, the tangent space of M and the space of one jets between the line and M, are CR minus one manifolds. And indeed, there is a natural map between them. If we consider a one jet, we can associate the following tangent vector, which is the result of evaluating the differential of f at the point x at the vector 1. And this is going to be a vector in the tangent space of M at the point f of x, right? Which is basically associating to a class of equivalence of curves its tangent vector, right? So what happens here is that this map is essentially forgetting the base point, right? This map associates to the class of equivalence of curves the tangent vector. Here we have that f of x is the value of it's the value by the target map that we cannot recover in any way the source. So this map is essentially forgetting the base point, okay? Now let us consider a definition, the definition of the R jet of F as a map. So given a CR map from N to N, we are going to define the following map, the map that associates to every point x of N the R jet of F at the point x, right? And what happens is that, again, we have a loss of differentiability. If M, N, and F are all of them CR plus S, then this map over here, in which we are considering derivatives up to order R, is of class CR plus S minus R. In other words, it is CS, right? So we always have this loss of differentiability. And what happens here is that if we consider F a CR map from M to N, then the R jet, it's going to be a continuous map from M to the space of R jets. In other words, but this is clear because if F is CR, then this map over here is C0, so it is continuous. It's a consequence of how the loss of differentiability works. So we get in this way a map which goes from the space of CR maps between two differentiable manifolds to the space of continuous maps between two differentiable manifolds. Of course, now the second manifold is this jet space, but it's still a manifold. And now we can try to generalize the results that we already have for a space of continuous maps, okay? by using this map over here. Let us see this theorem that is useful to generalize the results that we proved for spaces of continuous maps to the case of CR maps. The theorem says that the image of the map that we just defined, okay, is closed in the weak topology, okay? And we are going to consider just an example. That's a particular case because the general case, the proof is analogous. So consider R equal 1 and M and N are going to be the real line, right? And now consider a sequence of one-jets of C1 maps from the line to itself. Consider a sequence of one-jets that converge, right? Very good. Since the topology here is the topology of uniform convergence, that means that there exists a G, which is going to be a continuous map from the line to the line. Let's call it F. I think it's better. There exists a map F such that Fn converge to F uniformly on compact sets. All right. Now, there exists also a continuous map because of this convergence, okay, such that the derivatives of Fn converge to G also uniformly on compact sets. And what we want to show is that this limit of one jets is just the first jet of F. And in order to prove so, we need to see that the derivative of F is equal G, okay? Because in that way, it's going to be clear that the limit of the one jets of Fn is going to be the one jet of F, and F is going to be clearly C1. So, okay, what can we do in order to prove this? We have that we are considering the limit of the first jets of the sequence Fn, and Fn converge uniformly on compact sets to F and Gn, and the derivative of Fn converges also uniformly on compact sets to G. Very good. But now we can use that Fn applied to x is just the integral between 0 and x of the derivative of Fn, right? We're having this formula. And, okay, that's the fundamental theorem of calculus, if you like. And what we can do now is pass into the limit. And since the limits of, since these limits that we are considering are actually, this convergence that we are considering is uniform convergence in compact sets, and in particular the closed interval bounded by 0 and x is compact, what we get is that this equality passes to the limit. And so, okay, we have this for every x in the line and it implies that f of x is the integral between 0 and x of gt. But now we can use the fundamental theorem of calculus to obtain that the derivative of f at the point x is just g. And that's what we wanted to prove. So the image of this J super R map is indeed closed in the weak topology. The map J super R is also injective. This is because if two maps have the same RJets, in particular, the image by the target map of the RJ at every point is going to coincide for every point, and that implies in particular that the two maps are the same. So the map is clearly injective. And so we have a bijection between the space of CR maps, okay, and this space of continuous maps, or sorry, we have a bijection between this space of CR maps and the image of this map. The image is contained in a space of continuous maps and is closed in the weak topology, right? Since it is a subset of the space of continuous maps between two manifolds, we can consider in that subset the weak and the strong topologies. The topologies induced by the weak topology and the strong topology in this subset, okay? And by using the bijection, we can actually get two topologies in the space of CR maps. It is not difficult to check out that these two topologies are the weak and the strong CR topologies. So if we consider here the weak topology in this space of continuous maps, and we transport it to the space of CR maps between M and N by using this map over here, which is a bijection, we are going to obtain here the weak topology. And if we do the analogous construction with the strong topology for this space of continuous maps, we get here the strong topology for the space of CR maps, right? Okay. Now we get to the generalizations of the results we already have for the space of continuous maps. Consider M and N CR manifolds R is finite. Then the space of CR maps between M and N has a complete metric for the weak topology. And the reason is that if we consider the image by J super R of the space of CR maps is going to be a closed subset of this space of continuous maps in the weak topology. But this space of continuous maps is a complete metric space, and a closed subset of a complete metric space is also a complete metric space, right? So we just generalize the result for the spaces of continuous maps to the CR case. We have that every weakly closed subspace of the space of CR maps between M and N is a Verus space in the strong topology. Indeed, what we have to realize is that this map JR is a homomorphism for both the weak and strong topologies. Weak topologies in both spaces and strong topologies in both spaces. So what we have to check out is that the image of a weakly closed subset of the space of CR maps is also weakly closed. Right, but since this is a homomorphism for the weak topology, the image of a weakly closed CR weakly closed subset is going to be a weakly closed subset of the image. which is in itself weakly closed. So we have a closed subset of a closed set for the weak topology. And so that image is closed and we get the result, okay? We get that every weakly closed subspace of the space of CR maps is a Burr space. We can generalize this construction for infinity jets, let's say, but of course we're going to skip the details. What we get is that if M and N are C-infinity manifolds, then the space of C-infinity maps between M and N is a complete metric space for the weak topology, and with respect to the strong topology, we get that every weakly closed subspace of the space of C-infinity maps is a Burr space. Okay, these properties still hold true for the space of C-infinity maps. Let's see an application of this result. Consider M and N CR manifolds with R between 1 and infinity. And suppose that N is greater or equal than twice M plus 1, where this small m is the dimension of big M. If M is compact, then embeddings are dense for the strong topology in the space of CR maps. And in the case in which M is not compact, then embeddings are dense in the space of CR proper maps, right? An application is this more general version of the Whitney embedding theorem. If we have a CR manifold, a big M of dimension small m, this dimension can be embedded properly in R twice m plus 1, okay? And the idea is that we already saw that if we have a manifold, there exists F0, which is a proper map if the manifold CR is a CR function. It's a CR map from M to the real line. It is very easy to transform or to obtain a proper map from M to R to M plus 1, okay? So we consider N equal to M plus 1 and the manifold big M equal to R to M plus 1. And the map F, which is going to be a CR proper map from M to R to M plus 1, okay, whose first components F0 and the others can be anything, for instance, 0, right? This map's still proper. And so the theorem says that there exists that an embedding as close as we want to F in the strong topology. Okay, since the set of proper maps is open in the strong topology, that implies that there exists a proper map that is an embedding. Okay, and so we obtain what we wanted. There exists a proper embedding from the manifold big M to R to M plus 1, where small m is the dimension of big M. We introduced jet spaces in this lecture and we discussed their properties. At the end of the lecture, we studied a density result, namely that embeddings are dense in the set of CR proper maps. As a consequence of this result, we proved the general version of the Whitney embedding theorem, in which the manifold is not necessarily compact. In our next lecture, we are going to discuss the proof of the density of invariance in the set of CR proper maps. Thank you for your attention.